So example 7 asks us to use our binomial theorem to find the first 4 terms in the expansion of x plus 2y to the ninth in descending powers of x. So the binomial theorem says that we can actually find the values of our numbers, our coefficients in these expansions, using that notation that we used previously. So, for example, like our Pascal's triangle was 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and so on. And so how we do this is we take, like this represents row 0, row 1, row 2, row 3. So these numbers are actually, they look like this. So this is 0, 0. This is 1, 0. And this is 1, 1. This is 2, 0, 2, 1, and 2, 2. And this is 3, 0, 3, 1, 3, 2, and 3, 3. And so this is the pattern for how all of these numbers work. Okay, and what you'll notice is that the top number represents the row, or the, whatever the power that you're taking something to. The bottom refers to how many exponents off will that first part take, or how many, or will the second part take, or how many exponents off will the first part lose. So as we go back, so find the first 4 terms in this expansion. So we have 9 to the, this is to the 9th power. So we don't even have to know Pascal's triangle all the way down there. It's very inefficient to do that. So if we have x plus 2y to the 9th, we start out with 9, 0. X gets all of the power, so 9, and 2y gets none of the power. So instead of having to look up that number, we know what we can find. And so then we add to that. Now it's 9, choose 1. And we have x to the 8th. And now the 2y gets the 1. Notice how that is connected. Then we add 9, choose 2. So this would be x to the 7th, 2y to the 2nd. And then we add 9, 3. We have x to the 6th and 2y cubed. Notice how that works. So these are our 4. Sorry, I ran out of room a little bit. These are our 4 terms. And so now we just need to simplify them as best we can. So 9, choose 0. Again, like when we think about this, so this is going to be 9 factorial over 0 factorial and times 9 minus 0 factorial. This is the same thing. 9 factorial over 9 factorial. This just makes a 1. So we get 1 times x to the 9th. The 2y to the 0 makes 1. So then we add. We move on to the second part. So 9, choose 1. So this is, again, 9 factorial over 1 factorial times 9 minus 1 factorial. Well, 1 factorial is just 1. 9 minus 1 factorial, that's 8. So that's the same thing as like 8 factorial. Hey, well, 9 factorial over 8 factorial, that's just 9. And then we have x to the 8th, and then 2y. And we move along. So 9, choose 2. So this is now, and you see the pattern, 9 factorial over 2 factorial times 7 factorial. So we take, this is 9 times, so we can take this out. This becomes 9 times 8 over 2. So 9 times 8 over 2 is going to be 72 halves, which is 36. We have x to the 7th. We have 2y squared, so this is 4y squared. And then we have 9 choose 3. So that's 9 factorial over 3 factorial, 6 factorial. So this is the same thing as 9 times 8 times 7 over 3 times 2 times 1. So we can do a little simplifying here real quick. This is 3, this is 4, this is 7. So 3 times 4 times 7, 12 times 7 is going to make 84. 84 x to the 6th times 8y cubed. And then finally we simplify and put it all together. So we get x to the 9th plus, here this is going to be 18 x to the 8th times y. This makes 4 times 36 is 144. We have x to the 7th, y squared. And then we add 8 times 84, that's 640, 672, x to the 6th, y cubed. So this is the first 4 terms. We avoided an absolute headache of math by understanding this binomial theorem. This is really great practice for examining details and knowing how to shift and use rules and algorithms to our advantage. So in a problem like this, setting it up on top in the yellow where I have it is key, and then you just take it piece by piece to simplify on the way down. The more practice you get with the coefficients, the better. If you want to use your calculator for those numbers, that is also cool. That is 9, choose whatever you're looking for.